Okay, great. Thank you. So hello, I'm John. I'm the CEO of Veridise, and I'm going to talk to you today about a framework for creating new ZK domain-specific languages. So essentially, we're creating a new intermediate representation that can be used for ZK. So let's go and first talk about why we would want to do this. So basically, the reason why we want to create LLZK is because there's a lot of ZK DSLs. People are writing ZK in a lot of different languages. So some of them are here. So we have, very new specific DSLs like Circom, Zurgin, and Noir. But then we also have embedded DSLs where, the actual language is embedded into another general purpose language like ArcWorks or Plunky3 or O1JS. However, there's kind of an issue with this. And so the issue is there's a lot of kind of redundant work that needs to go into creating a ZK language, which is you actually need to create a front end. You need to compile down to normally an intermediate representation. You need to arithmetize your circuit. And then on top of that, there's a whole lot of things that people expect to come along with their language. And some of these are shown here. So for example, if you are a developer who's writing ZK, one thing that you might want is optimizations. You might want your language to automatically optimize your constraints. However, most of the ZK languages that we've looked at, don't really have optimizations. And on top of that, it's a little unclear what optimizations that they have. So for example, Circom says that they implement Gaussian elimination. Zurgin, the last time I looked, said that they do have some constraint optimizations, but it wasn't documented what they were. Halo 2 allows you to combine selectors, but that really just reduces the size of your proof. And Plunky 3, honestly, the last time I looked, I couldn't tell if they do any constraint optimizations, but they're still developing that, and so I'm sure at some point they will. If we look at other features like bug detection, Circom, Zurgin, and Halo 2 have bug detectors, but Plunky 3 doesn't. And then the types of tools that there are to detect bugs differ drastically between the languages. So for example, at Veridise, we have a static analyzer and a verifier for Circom. We just ported that over to Zurgin as well. If you're using Halo 2, you would have access to something like Halo 2 Analyzer, which can do some bug detection there. And as far as I'm aware, there aren't any bug detection tools currently for Plunky 3. Then if we look at hardware acceleration, which is very important for a lot of people when it comes to producing proofs, all of them have some form of hardware acceleration, but they differ pretty drastically in between languages. So for example, some of the languages like Circom focus more exclusively on CPU acceleration, whereas other languages like Plunky 3 focus a lot more on GPU acceleration. And so it's a little bit more difficult and nuanced in order to tell, which language is appropriate for me because, it depends highly on the device that you're working on and the context, and it's not kind of readily available to tell what is actually going to happen. And then finally, there's the supported arithmetization. So different arithmetizations, have different efficiencies. They've got different pros and cons based off of the proving systems that use them. And so, like Circom supports R1CS. It also technically supports Plunk. However, we've never seen anyone use Circom and Plunk. Zurgin supports R1CS and Air. Halo 2 supports Plunkish arithmetizations. And finally, Plunky 3 also supports Air. And so if we go and look at this, and one thing that this slide is trying to convey is that even if we look at these individual categories, like there's a lot of nuance into what a language is actually providing you. But on top of that, as people are writing these languages, they can introduce compiler bugs. So this is an example of a bug that if you've written Circom, you might be aware of, which is if you have an unused public input, it could be optimized out. And so with an unused public input, if you've written Circom, you've probably had to write a dummy square at some point, which is purely just to defend against a compiler bug, which it's unclear even now whether or not it's been fixed. And so with this fragmentation and little reuse in between components, it becomes much more likely that there's compiler bugs inside of each of these individual languages. And so The other thing that is interesting here is these ZK languages also share common vulnerabilities. And so that means that we don't necessarily need different bug detectors or verifiers to operate on each individual language because, one language is going to have one very specific type of bug and another language won't. A lot of the actual vulnerabilities that we see are common at a high level, but they might differ, when you look lower down at the specifics. And so this means that really for a security company like us, we should be able to target, just a common infrastructure in between all of them and implement tools once in order to, identify common types of bugs in ZK circuits. So that's why we created LLZK. So LLZK is an intermediate representation. It's not supposed to be a new language, and it's supposed to help. The slides are gone. Okay. Don't know what's going on there, but okay. Anyway, I'll just talk about LLZK. The slides will come back and everything will be perfect. Anyway, so LLZK is an intermediate representation where you're going to have a high-level language that compiles down to this certain representation of a circuit. This is common in between individual languages. So if you are building a new language, you only have to create a front end. And then if you are building a new proving system or something like that, you just have to implement a back end. And so the important part here is we're trying to create a separation of concerns. So if you're purely interested in trying to make ZK easier to write, you could just implement one component without having to implement the entire compiler architecture all over again. And so we can take a look at some of these features. So first of all, components that you create could be reused across a lot of different languages. They aren't specific to a single one. So this means things like transformations and optimizations that you implement in LLZK could be inherited by a lot of different languages, providing a lot more impact to a specific optimization. And drawing more people in because now, any optimization they implement is not specific to a unique ecosystem. On top of that, LLZK is implemented on top of this specific compiler infrastructure called MLIR, which is used a lot for machine learning. And the entire point of MLIR is the ability to create individual dialects. And so the reason why this is important is because as ZK continues to advance, like we've seen before, new features can be added into LLZK relatively easily by creating new dialects of this kind of base language, which can then be used to iteratively reduce down to a single language and then generate arithmetizations. So let's go ahead and take a look at this base dialect really quick. I'm running a little bit low on time, so I'm going to go through this super fast. So basically, the way that it works is subcircuits are organized into structs. Structs are going to contain two things. They're going to contain your code to do witness generation, as well as your constraints. And then all of the entries inside of your struct is the witness that is generated. So it's very clear exactly what an individual struct is going to generate, because it's going to fill in the witness. Then your compute portion is going to fill in your witness, and your constraint portion is going to, generate the constraints. So, yep, subcircuit witnesses must be explicitly declared. You can also declare some of them as pub in order to identify that it's a public input. Then structs can contain compute functions, and so a lot of ZK intermediate representations that we saw focus exclusively on constraints, but we also wanted to include the witness generator, because one, we can always farm that out to LLVM to actually compile. And two, we can actually do a better job of analyzing ZK circuits if we know what exactly the circuit was intended to do using generic computation. And then finally, structs are going to emit constraints. These constraints are what actually are going to constrain the computation within your ZK circuit. And then finally, sub-circuit inputs are passed into the compute and constrain functions both, and that's how you invoke them. So let's take a look at what this can enable. And so I mentioned earlier that you could reuse things like optimization passes. So let's take a look at that. For those of you who are familiar with num to bits, there's something very important, or with circom, there's something very important in the circom lib library when interacting with some of the templates. Basically, they didn't necessarily make the templates safe to use. They made them performant. And so this means that you can use them in unsafe ways. And so more specifically, one thing that you have to do here is if you want to create a safe less than circuit, you would actually need to invoke like num to bits in order to make sure your input is within a specific range. But circom leaves that out. The reason why they leave that out is because if you have already done a range check, they don't want to have to do that redundantly. However, with something like LLZK, you can actually look for redundant sub-circuit invocations relatively easily and optimize them out. And this is just because we can use a very easy property of ZK circuits, which is, they aren't stateful. They are pretty much entirely, or the behavior of them is pretty much entirely dependent on the given set of inputs as long as they're properly constrained. And so that just means that we can create a relatively simple optimization pass that would allow someone to create safe libraries and rely on an optimizer in order to optimize out redundant computation, which is something that you would expect normal programming languages to have. But so far, I don't think any do. The other thing that we can do pretty easily is implement tools. And so one thing that we can do here is we can do something like quickly verify output uniqueness. And so in this particular case, we don't need to worry about the compute function at all. We just need to look at the individual constraints and make sure that they actually create a deterministic computation. And so in this case, specifically, we can easily tell that out is underconstrained because it can be anything if A and B are 0. And so this kind of separation makes it very easy for you to write analyses as well that only operate on the important part of the circuit for your given analysis. And then finally, I mentioned that static analysis can be improved by looking at both the computation and constraints. And so the final thing that I'm going to look at here is just how static analysis might work. So basically, we can create a very easy static analysis here, where essentially we look at the side effects of the compute function and compare them to the constraint function. And you can see on the top in the compute function that out gets assigned to some value. However, when you go and compare the exact same computation, or what should encode or constrain the exact same computation and constrain, you can actually pretty easily see that out is never constrained. And so we can create these graphs that Veridise has published about previously, which allow you to encode both the constraint and the computation dependencies very easily in order to identify bugs relatively simply. And this makes it very obvious what goes into each individual portion, again, so you can just target the part of the computation that you care about. And so, yeah, that is pretty much everything about LLZK. And if you are working on a ZK language or are interested in implementing something like a new proving system, let's talk. Thank you.